Hello, this is a Physics 2212 Lab number 1, Charged Tapes. Introduction. The purpose of this lab was to observe the interaction of two charged pieces of tape and determine the magnitude of the electric charge on each tape as well as their electron deficiencies. This was done experimentally, then computationally using a Python program. And so the Python program was our model, and it was used to calculate the electric charge on each piece of tape, the number of electrons lost on each piece of tape, which was modeled as a point charge. Some of the fundamental physics principles that we used were Newton's second law, which was used to understand forces acting on each piece of tape, whether it was moving, whether it was stationary. Coulomb's law was also used to understand the electric force on each piece of tape. It was also used to be rearranged and solved for the electric charge on each piece of tape. The equation for the force of gravity near the surface of Earth was used to understand what exactly the magnitude of force of gravity was on each piece of tape. So using all those models and physics principles, we were able to achieve these results that are shown right here. So the method. So 2.2 meter pieces of tape or 8-inch pieces of tape, Scotch tape, were obtained. Tape B and tape A, you could say. They're taped down one at a time onto another 0.2 meter piece of tape stuck to the table. After a few seconds, the two pieces of tape were removed from the table. The sign of their charges was determined by bringing them near a pen rubbed with a piece of cloth to make it negative. Tape B was then suspended by two objects. Tape A was then slowly brought close to tape B from underneath, and their interaction and whether or not tape B floated was observed. That can be seen right here. The pen and the tape's interaction can be seen right here. And so in this experiment, the system was tape B, or the hanging tape. The surroundings was the Earth, and tape A. The initial conditions were the fact that the tape's length was 0.2 meters, the tape's width was 0.02 meters, and its mass was 2 times 10 to the negative 4 kilograms. So for the computational model part of this lab, a Python program was used in a software called Glowscript. And so the constants can be seen here, variables can be seen here, the lines of code used to visualize the pieces of tape can be seen here. And these lines of code right here are for calculating the force of gravity and equating that to the electric force so that we could solve for the charge on each piece of tape, which is then outputted right here. This model was also used to calculate the number of electrons that were lost, as well as the ratio of atoms to electrons lost, as well as the electric field and the electric force on tape B, or the hanging tape. So the results, what did we find? So we found that the tape B started to float when it was 0.0279 meters away from tape A. Using this value, we were able to plug it into Coulomb's law and solve for the charge on that piece of tape. It was 1.302 times 10 to the negative 8 coulombs. Using that, we were able to calculate the number of electrons that were lost, and this was found to be 8.1 times 10 to the 10 electrons. And so the ratio was 4.9 times 10 to the 6 as calculated manually. And when we ran the computational model, we found that the charge on each piece of tape was the same as was determined experimentally, and the number of electrons lost was the same as was determined experimentally. Other things were also calculated, such as the force of gravity, the electric field, and the electric force. And as can be seen right here, the electrons lost, the atom to electrons loss ratio was the same in the computational model and in the experiment. Discussion, additional questions, and conclusion. And so the main final result was the values were shared by the experimental data and the computational data. So this can be explained by the fact that they both use the same equations, and they both had one number plugged in, which was the distance between the two charged tapes when tape B started to flow. And to obtain these results, assumptions were made. For example, we treated the tapes as though they were point charges with all the charge evenly distributed throughout. We assumed that each piece of tape had about the same charge, and possible sources of error were treating the tapes as point charges, as we just discussed, unaccounted gain/loss in charge while handling tape, and rounding errors while calculating. But the chance of these affecting our results are pretty small. Additional questions. What if electrons had a positive charge and protons had a negative charge? What would change about the observations you made with your tapes and other charged objects? The observations would be the same regardless of charge. Like charges will always repel. Why is it important to handle the charged tapes as little as possible? What happens when the charged tapes come into contact with your hands or other objects? Making minimal contact was crucial. as to not transmit any unwanted charge to the tape which could mess up our calculations. Conclusion. So in conclusion, we observed that tape B began to flow 1.028 meters away from tape A. With this information and a few assumptions, we were able to calculate the charge on each piece of tape to be 1.3 times 10 to the negative 8 coulombs, and the number of electrons lost to be 8.1 times 10 to the 10. Ultimately, these obtained values were agreed upon by experimental calculations in the created